When we use linked list to implement queue, what we're having is an unbounded queue. This means that your underlying collection is not going to be constrained by a fixed size. Typically, in the case of an array, using linked base allows you to be flexible. You can basically just add to the end of the list whenever a new element needs to be inserted. You can delete any elements from the beginning of the queue using a link-based approach as well. It's simple as validating the initial node and repointing the head to the second nexus kin in that entire list. We're going to use LL node, linked list node, defined previously in the first chapter as our node class to grow queue. So this is the same LL node as what we use for stack. And then we're going to be discussing the link-based approaches as we compare queue implementation. This includes both implementation for enqueue and dequeue transformers, as well as the isempty, and the rest of it is actually the same. This is your linked queue implementation class that implements queue interface, generic interface. This linked queue has a whole bunch of member variables, front, rear, and number elements. So number elements the same as before. Each front and node is a reference. This is a two-pointer approach, one pointing to the front, which is right here, and one pointing to the rear, which is here. Note that both front and rear are both node instances. So when we point front to the very first node, the front itself is simply just a placeholder. It does not store anything. The actual elements that we are inserting into this list or this queue starts from here. This is node number 1, node number 2, number 3, and so on and so forth. The default constructor has both front and rear both set to null. In Java, any initialized reference object has a default value of null. Initially, this entire queue has no elements inside. This is the first transformer method. It's called enqueue. When we add something to a list, first of all, we have to create that node. This node is an element passed in. Then we insert the new node at the rear of the queue. We have two reference pointers, the front and the back of the queue. The front queue is always pointing to the very first element, and the rear queue is always at the back. If you're adding a new element, we have to create this node as a first step. And the second step is to ensure that the rear point to the new node, and then we'll have to increment the number of elements. These are the 3 steps. Second step simply does the linking itself, and number 3 is simply just repointing the rear. Even if the entire list is completely null, this approach also applies. Let's go through this general case here, double checking to make sure that the edge case, the linked list itself, is null if the mechanism 1, 2, 3, 4 also applies. Move on to the actual code. The node is created using this generic class with the elements being passed in. This element is the information that you want to capture. If rear is null, if you have an empty list where both front and rear are pointing to, so front is F, rear is R, both of these are pointing to null object, by default, this list is empty. When adding a new node to an empty list, you get one node, and this node is going to be pointed to by the front. Front is going to be pointing to this new node. This is the front. Your rear is going to be the new node. Well, because there's only one node, right? What if the rear is not null, meaning this list has some elements in it? This rear is already pointing here on the very end. This is the front, and this is the rear. So this list is not empty, and you want to do rear set link new nodes. This new node is created here. Set link is basically its next, pointing to the new node. This is the new one. And then what you need to do is making sure that this L points to this new. Rear equals new node. We'll take care of that business as well. Because we're adding a new element, the total number of elements is plus plus. This gives you 1 plus. This is how we use a generic node class to insert an element called enqueue at the end of your FIFO queue. Let's take a look at dequeue. Just like your enqueue, this is the exact opposite. We don't want to touch anything in the rear. One of the requisite is to decrement the number of elements. Dequeue means that first in, first out. The elements that needs to be removed is all the way at the front. Java has a garbage collector. You don't have to worry about deallocating this memory. All you need to do is to making sure that this number 2 option takes place to repoint front to this nexus kin over. So infos, which is your very first element, its next skin is right here. This becomes the new front. Set element to the information to the front node. DQ returns the information that you just removed. That information is in the info. In this particular implementation, the return object is the element itself. So this element could be a string. Number two is remove the front node from the queue. Front is now pointing to this new guy right here. If the queue is empty, basically one node inside this list. If that's the case, then you set the rear to null. So empty list calls for both rear and front to null. So if the queue is empty or null, both front and rear would have been set to null. Now, if the list is already empty, there's no more to DQ, and that is the runtime exception we were talking about earlier. Decrement the number of elements and return elements. Let's look at our implementations here. So this implementation is very straightforward. If the list itself is already empty, then you want to throw this because there is nothing to return. The second edge case is if the list only has one element. When you do front to front get link, if this is only one element strong, then it's terminator null. So your get link gonna get a null terminator. If front is null, you want to set the rear in null. When you remove an element from a list or a queue with only one element, you end up with null. And that list becomes empty. Both front and rear are null. One element queue, one node queue. What if your list got more than one node inside? This same algorithm is applied. First of all, your front get info gets you the information that you need to return. You return the element at the end. That's what you need to return. The number of elements is now decremented. The front equals front get links. This is your entire queue. Front used to point to this guy. Let's say this is A. You're dequeuing this. Your front is going to have to pointing to this. This is if there's more than one node available in this list. This takes care of the DQ methods. This completes the description of unbounded link-based implementation for queue.